Hi, good morning, everyone. I'm Jiayu, Assistant Professional Researcher at CBE. When the COVID-19 gradually fades away in our memory, the next pandemic may be just drawing near. Those public crises happen about every 15 years, let alone flus and influenza around us every day. Our buildings need to be ready with better solutions for them. Among those promising technologies, far-UVC is an exciting option for keeping the shared space safe from pathogens. However, there are still concerns remain for people to confidently put the device into their buildings. Today, I'm excited to share our team's assessment on the far-UVC system in the office setting, which was made possible by a great collaboration with LBNL and PNNL. So we know that some of the UV light can kill pathogens. The far-UVC is a specific type of UV operating at 222 nanometer wavelengths. The biggest advantage of these specific wavelengths is that it is safe for a human. While the traditional 255 nanometer UV system are restricted for the upper room applications, the far-UVC can be used in the occupied room when people are present, as they cannot penetrate skin or our eyes. They normally look like small boxes. You can easily put them on the ceiling or even on your desks. They normally cost only 2 to 15 watts of electricity to operate. The efficacy is similar to a medium to large size of a portable air cleaner, but much quieter as they don't make any noise. However, there are still concerns of far-UVC to be massively deployed in the spaces. The primary one is the generation of ozone. The high energy of 222 nanometer light can break the bond of oxygen molecule, creating atomic oxygen. Those separated atoms can further bond to other oxygen molecules to form ozone. Once those oxygen molecules, is that okay, great. So once those oxygen molecule bond with the separated oxygen atoms, they form the ozone. Those ozone can be very reactive. They can further react with volatile organic compounds and form secondary pollutant, such as formaldehyde and ultrafine particles. To understand if those chemical byproducts are the barrier to massively deploy those techniques into buildings, we need real-world data. Supported by Department of Energy, we converted one flex lab cell at a Berkeley lab to an open plan office. We brought in 4 to 6 human subjects to perform normal office tasks. While they were working, we alternatively switched the UV lamps on and off, and at the same time monitoring the ozone, ultrafine particle, and the VOC concentration in the room. After 3 months of intensive testing, we found that, well, those far-UVC lamps do generate ozone, but the increase is remarkably small. This plot shows that the ozone concentration measured in the room with the lamps off and on during, based on the night experiment during the daytime. We can see that the average increase of ozone concentration is just 1.4 part per billion ppb. When the room was empty, the increase of ozone was a bit higher at 1.1 ppb. This confirms that people are the sink of ozone. We absorbing some of the ozone from the air. During the nighttime, we observed the highest increase at 2.3 ppb. The day and night difference is caused by the nitric oxide level. We will explain that later. To make sense of how small increase it is, we can compare with the air quality index. It is not a very fair comparison as the air quality index, AQI, is designed for outdoor. So for ozone, anything below 60 actually is good. And over here, in Berkeley, the ozone concentration is around 30. So if you are outside or breathing from an open window, the concentration is way higher than those concentration we observed in the chamber. Well, for this tiny increase, we need very well-controlled chamber with very careful measurements to be able to quantify the tiny change. It is also quite meaningful. It is not only because we can ease the concern of ozone generation from far-UVC, and also we unveiled some interesting indoor air chemistry. One of them is a nitric oxide titration effect. The plot on the left shows that an example of what happened to that chemicals in the air when we switch on the lamps. Those light purple area are the period when the lamps were on. We can see that once the lamps were on and the ozone concentration, the dashed pink line goes up, and at the same time, the nitric oxide, the blue line, goes down, and the nitrogen dioxide goes up, the orange line. Through all the experiment, we quantify that there's a decrease, 1 ppb decrease of nitric oxide and the same level of increase of a nitrogen dioxide. For the secondary pollutant, we didn't observe any difference between the UV lamps on and off. Similarly, for the among the subjective feedback, we didn't see any statistical difference between these two conditions. To wrap up, our research demonstrated that far-UVC is safe regarding the chemical byproduct generation. It only elevates the ozone concentration in the single ppb level. It is because in the natural indoor element, such as the nitric oxide titration and human surfaces and other surfaces serve as a sink of the produced ozone. And we didn't observe any secondary pollutant at the level of concern. Thank you very much for your attention, and I think we have some time to take quick questions. For the further discussion, please feel free to join the breakout session later today. Thank you.